Okay guys, today you're all going to be learning about air, and you're going to be learning about how amazing this stuff is. Let's start off with what air is made of. If you could catch 100 molecules of air and put them in a box like this, then the chances are you would have 78 molecules of nitrogen, 21 molecules of oxygen, and 1 molecule of argon. Add them all up, that comes to a total of 100. The molecules are made up like this. The nitrogen molecule is made of 2 atoms joined together. The oxygen molecule is 2 atoms joined together, and the argon molecule is just 1 atom. Now, if you were to take a box of air and you pushed all the molecules into one corner, as much as you could, you compressed them as much as you could, all into one corner, the volume of those molecules would only take up 0.1% of the whole box. The rest of the box would be a vacuum, nothing in it. So basically what I'm saying is, even though the air molecules all around us, what's really around us is nothing, vacuum, because the molecules around us only take up 0.1%. But despite that, if we let the molecules roam around the box again, there are 2.7 times 10 to the 19 molecules per cubic centimeter. So in the air around us, that's the number of molecules there are. 2.7 times 10 to the 19 molecules per cubic centimeter. So try and imagine a cubic centimeter now, and there are 2.7 times 10 to the 19 molecules in there. Okay, go down a bit. So let's see what these molecules are doing in the air, or are doing around us. So the molecules are actually moving about very, very fast, and they're colliding into each other. Okay, if we were to take, for example, a nitrogen molecule, but it could be an oxygen molecule, an argon molecule, it would be moving at about 500 meters per second. I mean, that's faster than the speed of sound. The speed of sound is 340 meters per second. So, the average molecule in the air is moving around at 500 meters per second. It's really, really fast. Now, because they're moving around so fast, they're actually crashing into each other very frequently also. And in fact, they collide with each other 5 times in 1 nanosecond. So for each nanosecond, each molecule collides 5 times into another molecule, for example. Yes, each molecule collides 5 times in a nanosecond on average. So what is a nanosecond? Nano is 10 to the minus 9. 10 to the power of minus 9. So just so you can get a rough idea of what a nanosecond is, for example, light travels 30 centimeters in 1 nanosecond. Okay, so a molecule will crash 5 times in a nanosecond, but how far will the molecule actually travel? Yes, how far will it actually travel before it crashes into another molecule? And it will travel about 0.0001 millimeters before it crashes into another molecule. So now you should be able to imagine that these air molecules around you, nitrogen, argon, oxygen, even carbon dioxide, they're moving very, very fast. And they're moving very fast because they have energy, and this energy is actually heat. That's why they're moving around so fast. So they're not only moving around from one place to another, right? Each molecule is also rotating And they can rotate in 3 dimensions, of course. They can rotate this way, they can rotate this way, they can rotate this way, and of course they can rotate this way here. Okay, so we need to start talking about the carbon dioxide in the atmosphere. Actually, there's very little carbon dioxide in the atmosphere. At the moment it's 390 parts per million. Every year it's increasing by about 2 parts per million, so next year it'll be 392 parts per million, but this year it's 390 parts per million. But when you actually calculate it as a percentage, the CO2 in the atmosphere only makes up 0.04%. So, a very, very small amount indeed. One could call it a trace gas. So often people don't understand how can it be that such a small amount of carbon dioxide in the atmosphere causes global warming. And for that you need to go back and first see the previous lessons about how carbon dioxide vibrates in the atmosphere, and then perhaps come back to this video again. Just to remind you, the normal vibration frequency of carbon dioxide in the atmosphere for its bending moment is 700 centimeters. So when carbon dioxide starts to receive long-wave radiation or heat at a frequency of about 700 centimeters, it starts to vibrate like this. And we call this a bending vibration, because you can see the CO2 molecule is actually bending. As you can remember from the video before, this creates a dipole which creates more electromagnetic radiation, also at the vibrational frequency of 700 centimeters, and then the CO2 molecule starts to emit this long-wave radiation. But that still doesn't really explain how such a small amount of CO2 can heat all the Earth's atmosphere. And for that we need to go and we need to look at this diagram here. So this diagram here, here we show the CO2 molecule, and let's say there's some long-wave radiation coming up from the surface of the Earth. And you've got to remember that this long-wave radiation, it's permanently coming up from the surface of the Earth. So no matter where the carbon dioxide is, it can't escape actually the long-wave radiation. Now some of this long-wave radiation may have come from blocks of atmosphere either above or below this picture here. Some of the long-wave radiation might have actually come directly from the surface of the Earth. But all the time carbon dioxide is receiving long-wave radiation. Now, just like a tuning fork, if you hit a tuning fork and it begins to vibrate and emit a sound, well, in the same way, it's the same with CO2 as well. The long-wave radiation makes the CO2 molecule vibrate, and when it starts to vibrate, then it will too start to emit long-wave radiation out into the atmosphere. Then the long-wave radiation from this being emitted from this CO2 molecule will travel to other CO2 molecules and make them vibrate also. But this particular long-wave radiation being emitted is still being emitted at a frequency of 700 centimeters, and because of that, the long-wave radiation cannot make the oxygen molecules or the nitrogen molecules in the air vibrate at the same frequency, because oxygen and nitrogen do not vibrate at this frequency. Just like I mentioned earlier in the lesson, the molecules in the air are colliding with each other billions of times a second, and when they collide with each other, the vibrational energy from this CO2 molecule, when it makes contact, for example, with an oxygen molecule, through that contact it will transfer its heat, which is the same as its vibrational energy, to the oxygen molecule. Exactly the same with the nitrogen molecule. Yeah. In this diagram we have a carbon dioxide molecule, and the carbon dioxide molecule collides with the oxygen molecule, transferring its heat energy, its vibrational energy, to the oxygen molecule. And then in this picture we can see that the CO2 bounces off the oxygen molecule straight into a nitrogen molecule. And again, because the carbon dioxide molecule is continually receiving long-wave radiation, it also gains vibrational energy again, and when it collides with the nitrogen molecule, it transfers its vibrational energy, which is just heat, yes, to the nitrogen molecule. So now the oxygen and nitrogen molecules are vibrating more as well, and they will then go on to collide billions of times a second with other air molecules, transferring that heat to other molecules. So that's the process in which long-wave radiation via or through CO2 molecules manages to transmit its energy to the rest of the atmosphere. And it's a very efficient system too. So let me just summarize that again, explain it once again. For example, long-wave radiation comes up from the surface of the Earth. It is absorbed by a carbon dioxide molecule, which then starts to vibrate and itself starts to emit long-wave radiation. Now in the atmosphere, the molecules are colliding with each other billions of times a second, and when a CO2 molecule collides with an oxygen molecule, it transfers some of its heat energy over to the oxygen molecule. When the CO2 molecule then bounces off and collides into a nitrogen molecule, it will transfer the energy it's gained from the long-wave radiation. Yes, it will transfer this energy to the nitrogen molecule. Then the oxygen and the nitrogen molecules, they're vibrating more, they have more heat, and they immediately collide with other molecules in the air, other oxygen molecules, nitrogen molecules, argon molecules, and transfer their heat to those other molecules, thus heating up the whole atmosphere. Okay, I hope that's clear. Okay, see you next lesson.